Please. Okay, can you see my white screen, people? Can you see my white screen?
Yes, okay.
So, let me say a couple of words about, okay, this is about the lab report or random, let's call it random raw. Okay, now here we have an incoming waves. Okay, this is T and this is zeta. Okay, now with this signal, I'm going to provide with you a Fourier transform that I just implemented, and I calculate internally the Fourier transform of this signal, and we're going to have, okay, something like that. Now, this signal here, okay, was generated with a shaker. Now, the shaker was set up, you have to talk to Andy, between a frequency that I think it was 1 hertz, and the last frequency was, I'm not sure, you have to talk to Andy, I think it was 10 hertz. With these 3 frequencies, okay, because there was another intermediate here, that was set the motion of the piston. And because of the motion of the pistons, this surface generation was created. With this, we're going to calculate the spectral density of omega. So here, instead of omega, let's use F. Okay, so let's use this F. Okay, so we're gonna say F and this function of in hertz. So let's suppose that this is 1, and let's suppose that you check and that's 10. So this is the area or the range of the frequency in which we want to analyze the response of the chip, of the model, right? So we're going to have probably something like this. Okay, so more or less like this, because this is, remember, this is not something like that. And then this is going to be very small and very small in both directions. Something like that. So this is something that we are going to obtain from this time record of the test. Okay? Now, from that point, we could calculate the RAW. Let's ask somebody here. Go in order. Mr. Manrique, how do you calculate the RAW in the previous report? How do you calculate the RAW? Mr. Manrique?
Good morning, doctor.
No, good afternoon.
Good afternoon.
How did you calculate the RAW in the previous report? Barbara, do you remember how do you calculate the RAW in the previous report? Hidrobo, Miss Hidrobo, do you remember how to calculate the RAW?
Yeah.
Please, everybody, turn on your cameras because I need to see your faces. I need to see your faces. Then you're not. Isidro, do you remember how to calculate the RAW?
Yes, doctor. The response was the moment divided by the
Amplitude, because remember, rho is per unit wave amplitude.
yes.
Divided by Mr. Zambrano, you remember? Mr. Zambrano, can you continue? What do we have in the denominator?
It was the root square.
In general, this is complex. This is complex. So we still want the crude version of that expression. Ms. Lopez, do you remember? What do we have in the denominator?
The amplitude of the, no, I don't remember.
Amplitude is here. From the differential equation of motion. From the differential minus omega squared
Inertia virtual
Times the nature inertia.
plus
plus
displacement for GMT
displacement GMT and plus
E
I
frequency multiplied damping coefficient.
So this is, remember, this is complex in general, and we get the amplitude of that. So this is a function that probably will have a shape like this, right? About the natural frequency will be about here. Okay, so we're going to be working in the range between 1 and 10, more or less, more or less. And now you can combine these two and you can obtain the spectral density of, so this is rho. And we express as function of frequency, it's going to be equal to what? Do you remember? What's the expression for the spectral density of the response? Mr. Zamora, do you remember? No? Misayo, do you remember the expression for the spectral density of the response?
In this part, we use the ETTC and the other equation, the Pearson-Moscovitz.
No. This is equal to the spectral density of the incoming waves times rho squared. Okay, so this as units of length squared times time, and this as units of degrees per length, and this is squared. So we cancel this length, and the result will be in degrees squared times time. See, this is mostly theory. Now, let's go now to the measure that you took from the angle, the roll angle in the model. So in the experiment, you took theta as function of time. This is rho. This is expressed in degrees. So you have to convert the volts to degrees, and you got something like this. It's the same program as before. Okay, so we calculate the Fourier transform of this And with that, we calculate the spectral density, the response. Hopefully, probably there will be a large increment around the natural frequency, and there will be some other energies around here. So we have this is the spectral density from this measurement, from this time register. And this is the result of using theory. And hopefully, these two will be close. Okay. Any questions about these people? So all of these can be calculated using the knowledge from the previous report. And to do this, the calculations of the spectral density, I'm going to show you how to use a very small program. I just had the opportunity to complete, and that's it. No questions about it. Okay. So now, let me show you how can we analyze using a small program. This is not a big thing, really. Can you see my visual Fortran environment, people?
Yes. Sir.
Can you see? Okay, so I'm going to give you an executable. So when you execute, can you see my blue empty screen? Can you see my blue empty screen? No?
No, you can.
Okay, let me change. Now,
Yes.
okay, so this is what you are going to see. Okay, it's a simple screen. Type the name of the data file. Okay, I'm going to show you with an example. This is what I have right here. Okay, I generated a signal with a combination of 10 harmonics. So I'm going to say 10 harmonics. Then mix txt. Then they ask you for the name of the result file. For the name of the result file, what I usually do is I select any number that I want, but I add the extension EP, okay? Because the information that comes in the result file is the versus frequency. You have several functions, but it is already expressed to be presented or to be shown using EasyPlot. Okay, so let's say today is August 16.ep. That's the name of the result file. Now, he will ask you for the range of frequency where he is going to find the spectral density. Okay, in your case, okay, you have to talk to Andy, and he set up the spectral density of the motion of the shaker. I think it was between 1 and 10, but I'm not sure. In this case, I have a different range. So I started with a frequency very low, for example, 1.1 hertz. Clearly here you have the units. Let's go up to, for example, 10 hertz. And then we select an increment in frequency. So for each one of these increments, he will look for the content, harmonic content in the signal. Okay, and for example, you can use 0.01. That's 0.01 hertz. That's it. Okay, now I'm going to show you the result. Okay, so it was August 16. Can you see the easy plot figure? Directly, this is the result. Here, you have an explanation. Here, this is the name of the text file, of the data file. And on the right, this is the information on the time, it's 5:12 right now, and this is the month, day, and year. So if you run these times many occasions, you can identify different result files. Okay, and here you have each one of these signals. One is the real zeta. Remember, the program reads in the time domain. It does the Fourier transform. So you get real zeta star. So that's the real part of the Fourier transform. Imaginary zeta star, that's the imaginary part of the Fourier transform. Then it has the amplitude of zeta star. Remember, amplitude of the Fourier transform square, 2 pi divided by t, large T, that's the spectral density. In green, you have the spectral density. And also, I did a very simple approximation. So you got the Fourier transform, and from that, you can try to identify the amplitude zeta 01, zeta 02, etc., that you have in the content. So you have different functions. So I'm going to show you just the spectral density, okay? For that, what I do is I erase the lead curve. So the one that I'm going to show is just the green. So I'm going to erase all the other curves. The lead curve, this, the lead curve, that, and finally the lead curve, and this one here. So this is the spectral density. Okay. You can option auto range the whole graph. And this is exactly what I'm supposed to obtain, because remember that I employed 10 harmonics to generate this. Okay. This is what you need. So if you fit the elevation, a zeta, it will give you the spectral density of the elevation. If you run and you fit as a signal the roll angle, it will give you the spectral density of the roll angle response. Okay, in this case, I employed 10 harmonics, and you can count them. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So he's just finding the 10 harmonics that I put it to combine to generate the original signal. It's not magic, it's just pure calculations. Okay. Questions.
Doctor, a question.
Yeah, go on.
10 harmonic is a good number of harmonics.
No, I just wanted to see if the program was running correctly. So what I wanted from this exercise is to try to detect the amplitudes of the harmonics. And I was able to do it. I was able to do it. Okay. That's all. When I started doing this, that's all what I wanted to do. Okay. Yeah, that's all. They're not precise, absolutely precise, but they are quite good, really. So I am satisfied. In this case, I can show you the signal. Let me show you the signal, the original signal, so you can see its harmonics, 10 harmonics TXT. This is the signal, the original signal. This is 10 harmonics TXT. And if you open here, you see the details. And here you have 10 harmonics. Believe it or not, there are 10 harmonics in there. And when you do this spectral density, you can identify all of this information. Okay, that's the process that I want you to do. If there are some space next week, some of you, I would like you to participate in the Naval Engineering Technical Student sessions presenting this analysis. Okay, because it's a good idea that we start thinking about random. Every time you listen to the word random, you start looking at another direction, right? That happens to me. And what we have to do, we start just trying to start doing simple things. But this is the way we have to do it. Okay?
Doctor, for the next week, we present the project or the lab 3, the assignment 6.
If you are going to present your project in ship design, that's all your participation in the Naval Engineering Student Technical sessions. If you are not going to present that and you are in ship dynamics, I have to see how many slots do we have, how many opens do we have. Hopefully we will have 2. So those of you who are not going to present in ship design, you have to present either your project in ship dynamics or analysis of these random signals. I will chosen randomly, of course. We have to decide that by next Thursday. So then you will have time to complete the report and prepare. I can give you any feedback so you can present your results in a decent way. But it is something which is very important. See, when we started the ABET accreditation process, one of the first things that I realized was, what is a naval engineer? Naval engineer is a professional who can apply statistics and probability in the analysis of marine systems. Is capable of using hydrodynamics, structures, thermodynamics, materials in order to design a marine vehicle and marine system. That's the definition of what we are. Before designing a ship, you have to apply statistics and probability in order to analyze marine systems. It is defined by its name. That's the Society of Naval Architects and Marine Engineers in the US. So, and from that point, it was something extremely new for me. So that's why we need in general, our community needs to start. For example, when you do this inclining experiment, right? And you talk about the confiability of the result, that's good. You are aware that this calculation is not absolutely precise. Things like that. Every time you calculate something, you calculate average, and then you calculate also standard deviation. That means that how spread are the results. And now we can analyze, at least in a decent way, these random signals. Okay? Oh, people, it's too late. It's 5:26, and this is what we are going to do, okay? Either tonight or tomorrow, you have to come to Zoom, and you have to do by group, you have to do this progress of your project, okay? Do you have classes tonight? Do you have any class tonight? At
Yes,
what time do you
doctor,
have-
for design to 7 p.m.
Okay, yeah. In that case, tomorrow is Wednesday. I would like to listen to the presentations, to the progress of your groups. Okay, group 1. Who is in group 1? I can.
Zambrano, Delgado, e Hidro.
Let me open. Okay. Group 1, tomorrow. Do you want to do it tomorrow at what time? Early, please. 7 a.m. It's 3 minutes.
It's too early.
Too early? Okay, 7:10. Start at 7. People.
What's your disponibility schedule for just that hours?
Right now, the problem is this, people, is that Engineer Alejandro, he asks for permission for this week. So I'm right now working as a subdean. So I need to be doing administrative things. That's why I need to put you very early in the morning. So if somebody calls me for a meeting or something like that, I don't have anything to schedule for that. That's the reason I'm asking you. Or should I just randomly choose and set up this and schedule? It's just 1 hour because it takes 3 minutes for each group, so it doesn't take much. How about that? Okay, I'm going to do this random, and from 7:10 until 8 will be over. Mr. Zamora, do you have something specific?
Yeah, for my group, there's no problem to get the presentation at 7 p.m. 7 a.m. Sorry.
7 a.m. Okay, so your group, what number?
Group 3.
My group 3, Sayo and Barbara and me.
Okay, so 7 a.m. Okay, the rest of you, I'm going to set
Yes, doctor, my group
set
2,
in a random way. Yeah, who's this?
after group 3, in the 7:10 a.m.
Okay, but what's your number?
5.
That's my favorite number. Okay, 7:05.
Okay, 7:05.
7:05. Okay, the rest of you, I'm going to set randomly, and I'm going to post the itinerary tonight. Okay?
Doctor, just we do
Yeah,
the
go on.
after this class. I mean, after this session.
No, I don't think we have enough time,
Okay,
especially
okay.
since you have another class in a few seconds. So I don't want to do that. For we
Okay.
break, I'm just going to do that, and that will give you a couple of hours extra to prepare the presentation. Remember, it's just 3 minutes per group. It doesn't take much. So be efficient. Be efficient. Now, is there any group who is not going to participate in in ship design, who is not taking ship design? Any group who is not taking ship design? Any group who is not taking ship design, people? Any group who is not taking ship design? Everybody's taking ship design. Gutenberg and Vega, are you going to be working in as a group number 2, Gutenberg and Vega?
Yes.
So you're group 2.
Yeah.
Okay, in any way, I'm going to assign a random number to each group, and I'm going to post this itinerary for tomorrow. Remember, 3 minutes, that's all. Okay, if there's nothing else, that's all for today.
Okay,
Thank you,
doctor. Thanks.
Doctor.
You're welcome.
Thank you, doctor.
You're welcome.
Thanks.